So what's the fundamental theorem of arithmetic? It's basically just the fact that just like in computers, things are made out of variables. In math, numbers are made out of prime numbers. So for example, the number 24, we think of it as just one number, but it's made up of, it's actually a composite number made of a combination of several different prime numbers. So a prime number is something that is not one, but only has one and itself divided into it. So it's like an integer that is not one, but has only one and itself divided into it. One doesn't count because one is itself, so it doesn't really have two different numbers that divide into it. So what's the smallest prime number? It's actually 2, because 2 is the next number after 1. So by definition, it just automatically has itself and 1 divide into it. So 24 can be broken apart into 2 times 12, right? And then 2 times 12 can be broken apart into 2 again, 2 times 6. And 6 can be broken apart into 2 and 3. And now 3 is actually a prime number as well, because 2 does not go into 3. So only 1 and 3 goes into 3. So therefore it's a prime number. So the prime number decomposition of 24 is 2 times 2 times 2 times 3. Let's look at another number. Let's just say 20. 20 is equal to, what's the first prime number that goes into 20? 2. And can 10 break apart into? And now, is 5 a prime number, or is it a composite number that can be broken apart further? Prime. So let's write both of these numbers. So the total number of different primes that we found so far was 2, 3, and 5. And actually 4 is not a prime number because 2 goes into 4, which means that there's a number besides 1 in itself that goes into it. So the 3 primes that we found were 2, 3, and 5. And we had, how many 2's went into 24? So it's 2 to the third. How many 3's went into 24? 1. How many 5's went into 24? 0. And 20, how many of the prime number 2's went into it? 2. And how many of the prime number 3 went into it? 0. And how many of the prime number 5 went into it? 1. Now we could find more prime numbers after 5, like 7, for example. And we could write all the prime numbers going off to infinity and count up how many of them there were. But of course, 20 would have 0 of all the other prime numbers in it. And 24 would also have 0 of all the other prime numbers in it. So those other prime numbers don't really matter. But technically, though, if you counted up how many of each prime number are in 20 and 24, the result of that would be called the prime number decomposition of it. So if you take the minimum, sorry, let me spell minimum right. The minimum power, I'm just going to say the minimum number, because that's maybe easier to understand. The minimum number of each prime combined together you'll get the greatest common divisor. And then if you do the same thing, I'll just put quotes at the beginning, but you take the maximum number of each prime between the two numbers, then you'll get the least common multiple. So in other words, if you look at the powers, which are 3, 1, and 0, and 2, 0, and 1, if you take the minimum number of each one, then you combine that number of prime numbers together, you'll get the greatest common divisor. So let's go ahead and do that. What's the greatest? And it's called the GCD. What's the GCD of 24 and 20? So look at the which is bigger, 3 or 2? So look at those powers or the number of primes. There's three in the top one and 2 in the bottom one. Which is smaller? 2, right? And then look at the 3. Which is smaller, 1 or 0? 0. And look at the 5, which is smaller, 1 or 0? 0. So the GCD of 24 and 20 would be 2 to the 2, 3 to the 0, and 5 to the 0. What does that make? 4. Correct. Now the least common multiple of 24 and 20 would be equal to the maximum of each number of prime numbers. So now we ask which is bigger, 3 or 2? 3, right? And then look at the 3, which is bigger, 1 or 0? 1. And then look at the 5, which is bigger, 0 or 1? 1. So what is 2 to the third times 3 to the first times 5 to the first? It would be, yeah, something like that. So let's just check. 3 times 4 is 12 times 10. I think it's actually 120.
Yes. Yeah.
So we got the GCD is 4, the LCM is 120. Now that's actually a very tedious process because you have to find all the prime numbers. So imagine doing this with a number like 1,000 or 1,100 or 1,800 or something like that. You could spend 10 or 15 minutes just finding the prime numbers, all the prime numbers that went into each number. And of course, theoretically in math, this is a very simple definition. The GCD is just the smaller numbers that are in common. The LCM is just the biggest number that's the biggest power of each possible combination of powers. So is there any better way of doing this? Well, first of all, there's a slightly better way of understanding it, maybe more intuitively, that I can show you. And then there's like an algorithm for finding, at least for finding the LCM, at least. No, not the LCM, the GCD. So first, let's talk about the these same numbers, 24 and 20 on another page. So let's play a little game called the find the common and the uncommon factors. So look at those, both of those numbers. Find numbers that are in common to them. And then after that, write down what's left over, which is called what's uncommon. So think of one number that's in common to both, that's a common factor that divides into both 24 and 20. Could be small or big, in fact, start with the smallest one, 2, right? Once you write that down, then you cross that out. So this is like a game to see who can get to the end first. So cross out 2 from 24 and you're left with 12. And cross out 2 from 20 and you're only left with 10. So like who's ahead now? Well, let's see. Is there any other common factor that's in both? Another 2, right? So write down another 2. Cross out a 2 from 12 and then you're left with 6. Cross out a 2 from 10 and then you're left with 5. Is there anything else that's in common? Well, there is a 2 and 6, but there's no longer a 2 left in the 5. So there isn't even 2 or 3 or anything that's in common now. So left over is 6 and 5. So if you multiply together only the common ones, 2 times 2 equals 4, you'll get the greatest common divisor. The greatest common divisor is equal to the product of the common factors, basically. And then the leftovers ones, if you take, what is 6 times 5? That's 30, right? If you take the number 4 times 30, you'll get 120. The least common multiple is equal to the product of the common factors that you found times the leftovers, which I call the uncommon factors. So basically just the common ones is equal to the GCD, but the common ones times the leftovers equals the LCM. So that's another way of thinking about it that maybe doesn't involve so many steps, because you don't have to necessarily find the prime numbers. You can find anything that's in common, cancel it out, and then make it smaller and smaller until there's nothing in common. And then just multiply everything in common times what's left over to get the LCM. And then multiply everything that's in common without the leftovers to get the GCD. Okay, well, now we get to this exciting process though. So this process only kind of makes sense if you have really big numbers. But we can try the process on 24 and 20 though. So let's say you're trying to find the greatest common divisor of 24 and 20 without finding the prime numbers and so forth that went into it. So we're going to replace the bigger of those two numbers with a smaller number and keep the smaller one. So we'd like to reduce this problem. Sorry, hold on. I didn't mean to say implies, I meant to say equals. We'd like to reduce this problem to the GCD of 20 and then something smaller than 20. So what legally are we allowed to replace the 24 with? So remember we just learned about modular arithmetic, right? We can actually replace the bigger number with the with the bigger number mod the smaller number. So it's 24 mod 20. So what's the remainder of 24 if you divide it by 20? So how much is left over? How much bigger is 24 than 20? 4, right? So the GCD of 24 and 20 is the same as the GCD of 20 and 4, right? Now, this process works until you have a remainder of 0. So once you have a remainder of 0, then you actually have to find what the common factor is. So it does not, you can't say that the GCD of 20 and 4 is equal to the GCD of 4 and 0, for example. So you cannot say, because you can't divide by 0 basically, but you cannot say that this equals the GCD of 4 and 0. But that shortcut works as long as you don't get a remainder of 0. So we can't go any further than that. But what's the GCD of 20 and 4? Well, guess what? As soon as you get to a number that actually does go into the other number, then that's the answer. So poof, the answer is just 4. So that was easy, wasn't it? So let me explain why. Like, what if you had said, what's the GCD of 4 and 8? Anytime you have a smaller number and a bigger number, and the smaller number actually goes into the bigger number, then the greatest common divisor is just equal to the smaller number. Smaller number, which equals 4. That's only true if the smaller number actually goes into the bigger number. So your goal is to try to get to a number that actually is so small that it goes into the biggest number that's left. Once you get to that number, then that itself is the greatest common divisor. So let's try this with another slightly bigger number. Let's see. Okay, somebody give me a prime number between 5 to 10. 7. Okay, somebody give me a different prime number between 5 to 10. Well, I guess there's not really any other ones other than 5. Okay, we'll just do 5. 7 times 5 is 35. Okay, now give me a prime number between 10 to 15. What's the prime number that's between 10 to 15? 11. Now let's multiply that by 7, because we're going to have one prime number that's in common. 11 times 7 is 77. So let's try to find out. Obviously, we can see the prime numbers are 7 and 5 and 11 and 7. So what's the greatest common divisor actually going to be between 35 and 77? It's going to be 7, because that's the prime number that they have in common. But let's pretend that we didn't know that, though. What's the greatest common divisor of, let's start with the biggest one. Sorry, my fault. Now, you don't really have to start with the biggest one, because the GCD of 35 and 77 is the same as the GCD of 77 and 35. But I just like to start with the biggest one so that it's just in order. So the GCD of 77 and 35 is the same as the GCD of 35. And now how do we replace the 77 with something smaller than 77? You replace it with a remainder if you divided 35 into 77. Remember, you place the bigger number of the GCD pair of the pair of numbers you're trying to find the GCD of. You replace the bigger number with the remainder of dividing the bigger number by the smaller number. So you basically replace 77 gets replaced with 77 mod 35. So what is 77 mod 35? Well, 35 times 2 is 70, right? So what's the remainder after getting 70? 7, correct. So the GCD of 7735 is the same as the GCD of 35 and 7. And now the 7 goes into 35, right? So that means that now we're done. Whenever you get to a number that's so small it goes into the other number, then that number itself is the GCD. Poof, like that. So that was kind of cool. Now, the way the book explains it looks a lot more complicated because this is all based on stuff that people wrote down, like the ancient Greeks and things like that. So let me see if I can show you the page to it. But I'm just explaining to you what's really going on. And then the book teaches it to you in like some sort of a strange mathematical way, which math is good. It's just you have to get a lot of practice reading the math to understand what it's really saying. Just a second. Where is that? It's called Euclid's algorithm. I'm trying to find it. The Euclidean algorithm. Okay. Okay, so let's try to do example 16, for example, on page 284. So page 284. This is not an exercise, this is just an example from the book. Example 16. And it says to find the GCD of 414 and 600. Hold on, let me reverse the order of it. By the way, they don't actually think of it the same way that I do, because they're not really thinking of it from a programming point of view. But GCD of 662, 414. So let's put the bigger one first, and then the smaller one. And then now the way we would do with my method is to try to shift the smaller one over to come first, then replace the one after the smaller one with an even smaller one. So the way that the book teaches it is like this. It's really weird. So 662 equals. So they divide 414 into 662. How many times does 414 go into 662? Only once. So this is 414 times 1 plus what's the remainder? So how do I find the remainder after dividing 414 into it? Well, 414 times 1 is just 414. So I have to subtract 414 from 662 to get the remainder. So there's a lot of hold on, let me move my calculator out of this box. Okay, there we go. Okay, so what is 662 minus 414? Just to figure out what the remainder is. 248. Yep. So that means that the GCD of 662, 414 is the same as, let's shift the smaller one to become the bigger one. And let's replace the 414 with 248, because that's the remainder. So the GCD of 662, 414 can reduce down to the GCD of 414 and 248. That's because the remainder is 248. After you divide 414 into 662, which goes in once, the remainder is 248. Now, by the way, this one doesn't matter. This one doesn't matter. So this number right here and this number right here, that's the pair of numbers that you're now working with. It does not matter whatsoever how many times the smaller number goes into the bigger number. The smaller number might go into the bigger number 1,000 times or one time. It really makes no difference. The only thing that matters is that you keep the smaller number and you keep the remainder after dividing by the smaller number. Now we're going to forget about the 662 completely, and we're going to work with the bigger number. So which number is bigger, 414 or 248? 414, right? So we're going to take the 414 and we're going to divide it by the smaller number, which is 248. How many times does 248 go into 414? Once. So you just say, now this is the part that I don't like, writing it all out like a whole huge bunch of arithmetic problems. So 414 is because these arithmetic problems don't really matter. Like, it doesn't really matter how many times 248 goes into it. The only thing that matters is what the remainder is. So 248 goes into 414 once, and then after you subtract that from 414, what is 414 minus 248? Well, let me just make sure about something. Okay, good. What is 414 minus 248? 166. So the remainder is what matters, 166. So this one isn't important. It doesn't matter how many times 248 goes into 414. The only thing is you're going to keep the 248, which is a smaller number. Well, let me do a box around those. You're going to keep the smaller number, which is 248. Whoops, I don't have enough space. Keep the smaller number, which is 248. Whoops. And you're going to place the bigger number with an even smaller number, which is the remainder, after dividing the bigger number by the smaller number. So now we're going to break down the bigger number, 248, and divide it by the smaller number, which is 166. So how many times does 166 go into 248? Once. So 248 is equal to a division of 166 times 1. So what's 248 minus 166 to get the remainder? 82, okay. So 248 minus 166 is 82. So the remainder is 82. So that means the GCD of 248, 166, I can shift the 166 to the left, 166, and replace the 248. So now 166 is the bigger number now, and the smaller number is only 82. That's the remainder of after dividing the bigger number by the smaller number. Then I'm going to go ahead and work with the bigger number, 166, to try to get rid of that. And I'm going to take the smaller number, divide it into the bigger number. So how many times does 82 go into 166? I believe twice. So 82 times 2, 80 times 2 is 160. 2 times 2 is 4. So that would give you 164. So if you have 164 divided into 166, what's the remainder? 2, correct. There's 2 left over. So that means the GCD of 166, 82 can be shifted over to be the GCD of 82 and 2. Now at this point, does 2 actually go evenly into 82? Yes. So once you get to a small number that's so small, it actually goes into the first number, then that number is the final answer. So the GCD equals 2. The GCD of 662 and 414 is 2. Notice we did not find a single prime number that went into any of those numbers. Like, none of these numbers up there are probably prime numbers, but we still found the greatest common divisor. So this is not a very constructive way of doing it, but it's a very incredible way of doing it, as long as you don't have to write out all the arithmetic like that. So thankfully, with a computer has most computer languages have a symbol that represents mod. Basically, you just say do something. This is like in pseudocode, basically. But basically, while the bigger number is not evenly divisible by the smaller number, replace the bigger number by the bigger mod the smaller. So, and then of course, once the bigger number is evenly divisible by the smaller number, when finished, the final smaller number is the GCD, like that. So that's pretty cool. So that actually makes it very easy to write a computer program that can compute the GCD of two numbers. Let me think. Let's go ahead and work on some of these. Okay, let's just see. Okay, perfect. Let me assign to you. Okay, so for your homework, I'm going to assign this is section 4.3, and this is page 4.3. The exercises start on page 288, although our first problem won't actually be until 289. So page 289, that's where our problems will start. And we're going to start with number 24. Number 24. And then I also want to assign you well, they don't have very many of these questions available as options. They only have two. They only have two. Okay, well, let's just do 32, number 32, since they don't have the answers to that in the back. But I'm going to give you a little bit of help with it, though. So on 32, you only have to actually show your work on. So show your work like what we did a few seconds ago. Remember when I was doing the where is that one? So did I write that down? I guess I erased that page, but remember when I was showing those equations and things like that? So show your work with the equations. Show your work with the equations for on 32. Show your work with the equations on A, B, and C. But then I'll let you use a computer function that I'm going to try to help you with right now. Use computer. So you can't just go to the internet and like look the answer up, but you can use a line of computer code to do the last three. The last three. Okay, so let's work on that line of computer code a little bit. I don't know why I erased that page. Oh well. So show your work with the equations for ABC and then use the line of code for the last three, because they're really big numbers. Like you're supposed to find the GCD of like 1,000 and 50, 40 and things like that. So let's go ahead to a cool website that there is. Actually, all of you have browsers, right? Which browsers do you use? Like, do you use Chrome? Do you use Internet Edge or whatever? If you push F11 on your if you push F11 on your keyboard, at least with some browsers, it'll bring up like a coding console, and you can just write code into it. Another option you can do is but I'm going to help you with the code. All you have to do is just use my line of code and change the numbers in it. So let me go ahead and stop sharing this window. Hold on just a second. Stop share. And then I'm going to go to this window. Wait, what's wrong with this thing? Okay, there we go. So why is this thing? Oh, okay, there we go. There's a website called jsfiddle.net. And how do you make this thing go away? I think something's wrong with this computer because they have been behind on software updates. Wait, I think Chrome has just completely crashed. Let me try again. Okay, there we go. Okay, yeah, here it's working now. Okay, so share screen. So let's try to write a line of code or a couple lines of code that have that functionality in them. So we'd like to write a code called GCD. There we go. Oh, there it is, X. Okay. GCD that takes two numbers, A and B, and it calculates their greatest common divisor. So first, I don't want your computers to go into an infinite loop when you type in this code. So I'm going to put a loop around it for I equals 0, I is less than 10, I plus plus. And then I'm going to put two curly braces around that. That way it'll never run more than 10 times just as a safety measure. But we could replace a 10 maybe with 20, just this still wouldn't crash. If you have a loop that has like one syntax error and you don't have the right, if it doesn't have if it runs on a condition like if the remainder is 0, for example, and if something goes wrong, it can accidentally run forever. So let's just put that in, and then we'll have a variable called big and small. So variable big equals the maximum math.max of A and B, and variable small equals math.min of A and B, like that. Perfect. All right, so then we're going to do this. We're going to say, if, how do you calculate mod in this language? In a regular web page that uses JavaScript, you use the % symbol. So we're going to say if big mod small equals 0, then break. That means the loop is going to stop. And then at the end of the loop, after the loop is over, we're going to return the small number like that. So the code is almost done now already. We need to add in one more line after that if statement though. What line should we add into that if statement to make this the final step of logic to make this work? So remember, we're going to if you remember that logic that I was doing in this method that how I was explaining that it worked to you. We had two numbers. We were trying to find the GCD of them, and I always put the biggest one in the left side, right? Now mathematically, you could do them in either side because you could be left-handed or right-handed. It doesn't matter. But so if you found the remainder after dividing the big by the small, then you could replace the big one with the smaller previous one, right? And then you could get a new one that was even smaller, right? So let's just say this real quick. Ready? So if the big, actually, I'm going to have to use a variable real quick. So I'm going to add one more line before that if statement. So the remainder of it is big mod small, right? That's the remainder. So then I'm going to replace this and say if the remainder is 0, then break, right? Otherwise, we're going to replace the big one with the small one, right? And we're going to replace the small one with the remainder, like that. Did I spell all those variables right? So what we're going to do in each step of this process is we're going to calculate the remainder. The big number modulo the small number, which is the remainder after dividing by them. And I forgot, oops. Okay, that's supposed to be double equals. Is that double equals? Yeah. So double equals. Okay. So if now, by the way, use a double equals in programming to check if something is true. So if the remainder is double equal to 0, that means if it's equal to 0, then you're going to stop the loop. Otherwise, if it's not equal to 0, then you're going to set the big one equal to the smaller one that you previously had. And then you're going to replace the smaller one with the remainder of dividing the big one by the small one. So does that logic make sense to you? Okay, let's test this out. So we're going to say alert GCD of 20 and 24. So who remembers what the GCD of 20 and 24 is supposed to be? 4, I believe, right? So it says we got 4. So calculate the GCD of 20 and 24 was 4. It seems to work. Let's try with something else. By the way, if you don't want to alert something each time, you can also just say document.write. Like this. So document.write. That just puts the number 4 into the output document. Let's try. What's a bigger set of numbers we can find the GCD of? Does anybody remember one of the other problems we did? How about what's 7 times 5? 35, right? And what's 7 times 4? 28. So the GCD of 35 and 28 should be 7, right? That seems to work. Let's find something that's a little more complicated. What give me 2 prime numbers. Oh, I didn't actually think about prime numbers, huh? So like 7 and 11. It'll be interesting to see if it actually works with prime numbers. Let's try 7 and 13. Okay, it actually worked. Wow, it's incredible. I didn't have that much faith in it. So what's the biggest number that goes into 2 different prime numbers? 1, right? Because prime numbers don't have any number that goes into them except for themselves and 1. So the smallest number, the biggest number that's in common to both 7 and 13 is 1. And it worked. So, it seems to work no matter what. But let's try it with some really big numbers, though. Let's try with those numbers in the example that we just did a few minutes ago. 414 and 662. So let's try that. 2, it worked. So it gets the same answer for everything that I can think of. Now, of course, there could still possibly be some bug in it that I didn't think about, but it should work. So do all of you understand the logic in that code? The function starts out, it accepts 2 parameters, 2 numbers, A and B. First of all, it has to know which one's bigger and which one's smaller. So calculates the bigger one, which is the maximum of the 2 numbers, calculates the smaller one, which is the minimum of the 2 numbers. And then just for safety, it has this loop. Now, by the way, this is extremely dangerous. I don't recommend doing loops that could run to infinity. So you could actually take all this stuff out and replace it with 2 semicolons like this. That's called sometimes they call this a server loop. If you have a loop that runs forever like this. This won't actually run forever because remember, whenever it gets to a remainder of 0, it will break. But that's very dangerous to do because what if some hacker plugs in like negative numbers or plugs in 0 or something like that into that loop and it puts in some input that it's not designed to have, or they put in a decimal number. So I wouldn't recommend taking out that. By the way, the I variable doesn't have anything to do with what we're doing. Like we're never using the I variable at all in any of this code. The only reason I said it goes from 1 through 20 is just to make sure that that loop will only run at most 20 times to stop it from going forever. Otherwise, somebody could put in something maybe like a weird decimal digit or something like that that would cause the computer code to crash. And then that loop would run forever. Then you'd have to unplug your computer or turn the power off or restart your system. So whenever you write computer code, always think of the worst case scenario and try to make your computer code not crash, even in the worst case. So I'm going to save this fiddle. All you do is just do Control S, and it creates a URL for us. As soon as you save it, it creates a URL. All of you can go to this URL right there, jsfiddle.p9u-log-y1/8. And when you're doing your code, all you have to do is to go down to this last line of code right there and just paste it several more times, and then paste in the numbers that you have. Like, let's say if your homework problem, now of course you have the same homework problem, so you're going to do the same thing. Promise not to actually just copy from each other though, but do like GCD. Let's say if the homework problem says find the GCD of 252 and 198. So 252 and 198. So then you'd change that line of code to say 252 and 198, and then you'd run it, and then it says 18, which is the correct answer. So once you run the line of code, you find GCD of 252 and 198. Then you can put that answer to your homework. And I won't necessarily ask you to submit your code, but I'll probably go check and like maybe look at how many hits and things got on this website. There might even be a way of actually, why don't you do this? Since you're all going to be using the same file right here, the version that I have is version number 8. See, it says LOGY version number 8. So that's the one that you are all going to start with. Every time you do your homework, just push Control S again like that. That'll save a new version of it, like number 9. So then I can go back and look through those versions and make sure. In fact, why don't you put your name and the version that you're doing? Like if I go down here and put a comment in that says /* and just say, like Bill Smith /. In fact, you could put it up here in the HTML section like this, Bill Smith. That way you don't need to put a comment around it. So that will just have the word Bill Smith. Whoops, maybe not. Yeah, but at least I can see that word Bill Smith. So if I go to version number 10 right now, I can see that says Bill Smith. Like that. So you can do your work once you're done with your work, just put your name at the top of it, and then I can look through your work. But then everybody else can go back to version number 8, and then that won't have that work on it. It'll just start with this. So how does that sound? So you can take a picture of that link if you want to, or I can also maybe put the link into Moodle. Let me go ahead and put the link into Moodle. So that's your homework for next week, is those 2 problems. And you can turn those in, let me think. I guess I'll go ahead and give you until Monday evening. Just make sure that you all upload them into the assignment that I'm going to add to Moodle, and then I'll grade those 2 problems. Hold on, let me just make sure I get this added into the Moodle shell. So okay, for some reason the window doesn't work quite right when I'm recording. Hold on, let me stop the share. There we go. Okay, so that's the end of the meeting. I'm just going to add that link to Moodle, and then